Okay, number 5 on page 20. So you have 1,800 meters of fencing available to fence 6 identical pens, as in the diagram. Explain why 9x plus 8y equals 1,800. Okay, so one good thing about IB problems, and sometimes in the book problems, is when they give you one of these problems, they don't just like throw it out there and expect you to do the thing from beginning to end without any hints. So they break it up into steps and they kind of walk you through it. Sometimes in the book they don't do that very well. They just like ask you to go all the way to the end. Explain why 9x plus 8y equals 1,800. Well, look at what x and y are. X and y are lengths of fence. 1,800 happens to be the total amount of fencing available. So what they're just saying is if you add up all the fence in the drawing, it should equal 1,800. So you say, okay, how many x lengths are there? There's this one here, and since these are all identical rectangles, I just count how many x's there are. And there are 9x lengths, right? So I'm going to say, okay, 9 lengths of x. And what about lengths y? So there's 1, 2, 3, 4, 5, 6, 7, 8. And so there's 8 lengths of y. So that's why it becomes 9x plus 8y is the total fence, which is 1,800. Okay? All right. B. Show that the area of each pen is given by A equals, and then that terrible expression there. Okay, so we remember that whenever you do one of these optimization problems, you need 2 equations. And normally the equations for spatial problems would be perimeter, volume, or area. And in this case, we're talking about a 2-dimensional thing, so we're not going to do volume. So the other equation must have to do with area. And yes, indeed, they do ask us what the area is. So area is normally length times width, right? So you're like, oh, okay. So that the area of this whole thing would be 3x times 2y. But in this particular case, they're saying the area of each pen. So like each one of these 6 pens has a certain area, and the area is going to be xy, right? And it's like, oh, that was easy. A equals xy. But now they want us to put it in terms of x only, meaning we have a y here. They don't want the y. They only want x's. So is it possible to eliminate that y somehow? Okay, now we go. Remember in the previous problem, I gave you the steps to do an optimization problem. First thing you need is 2 equations, and we do have 2 equations now. We have an area equation and we have a perimeter equation. Then they say, which is the optimization equation? Okay, the optimization equation is the one that we were trying to make the smallest or biggest possible. Okay, we don't know that yet. If we look at this part C, we'll know if the area enclosed is to be maximized. So if the area is to be maximized, so that we know that this must be the optimization equation, right? Which means that this is the constraint equation. Okay, so the constraint equation is the perimeter equation. And then, so we know what the constraint equation is. It asks us to solve for y in the constraint equation. Sometimes you're solving for x, whatever you're trying to eliminate, right? We're trying to eliminate y. So we're going to solve the constraint equation for y, and then we're going to use that to eliminate the y, okay? So maybe you don't understand what I'm saying, but just go ahead and solve for y first. So it's 9x plus 8y equals 1,800 because the total fence is 1,800. One of the ways you can identify what the constraint equation is the constraint equation only has 2 variables. And at the beginning, the optimization equation usually has 3 variables. 3 variables. I'm sorry, it's x and y. So A, x, and y are the 3 variables for optimization. We don't know what area is, and we don't know what x and y are. In the constraint equation, we know what the perimeter is, 1,800. So that's why it becomes a constraint equation. We get a specific value of perimeter to use. That's why it's constrained. So we're going to solve for y. So the way we do that was we subtract 9x from both sides. So we get 8x equals 1800 minus 9x. Then we divide both sides by 8. So we get y equals 1800 divided by 8 minus 9/8 x. 1800 divided by 8, that is equal to 225. You can do that with your offline calculator. 225 minus 9/8x. Okay, and then I'm going to take this expression for y and I'm going to substitute into a equals xy so that we don't have any more y's in the equation. So it's x times 225 minus 9/8 x. And then if I expand this, if I distribute the x, I would get a equals 225x minus 9/8 x squared. And now I've got what I was looking for. It's just in the opposite order, right? C, if the area enclosed is to be maximized, what are the dimensions of the pen? Okay, so in this particular case, let's show how to do it without the calculator first, and then maybe we'll do it with the calculator. So this is an upside down parabola, right? Because the a value, or let's look at this one, it's a little bit easier. The a value, which is the value that's multiplied times x squared, is a negative number. So that means that this is an upside down parabola. And the parabola represents the area, and the maximum value of area, of course, would be this highest point here. In an upside down parabola, the highest point is the vertex. So the way you solve these particular problems, where they're optimization problems with parabolas, is you're going to find the vertex of the parabola, which we know how to do. What was the procedure to find the vertex of a parabola again? It's to find the axis of symmetry using x equals negative b over 2a. So what's our a? Our a is the number that's multiplied times x squared. B is the number that's multiplied times x. And what's our c in this case? It's 0. There is no c. Okay? And so we can put x equals negative b over 2a. That would be the x value, which makes the parabola have the maximum value. So we'll have negative 225 divided by 2 times negative 9/8. So we'll have negative 225, and then 2 cancels with 8, and so to get 4, so we get negative 9/4 on the bottom, right, instead. And remember that if you have a negative number divided by a negative number, you get a positive number. And if you divide by a fraction, you multiply by the reciprocal. So this is equal to 225 times 4/9. And 225 times 4/9 is equal to, 225 times 4 is equal to 900. 900. And 900 divided by 9 is equal to 100. So it turns out that the x value is 100. And they want to know the dimensions of each pen. So how would we find the dimension? We're saying that the yellow dimension is 100. What is the blue dimension? The blue dimension, remember, we have an expression for that. It's y equals 225 minus 9/8 x squared. So we can find y by substituting 100 in here. So we have 225 minus, oh, it's not x squared, it's just x. 9/8 x. So 9/8 times 100. So we get y equals 225 minus 112.5. 225 minus 112.5 is, I didn't do that in my head, I did it with the calculator, by the way. 225 minus 112.5. 112.5 is exactly half of 225, so when you subtract it, you get 112.5 also. So the dimensions of each pen are 100 by 112.5. Okay, and so that makes the area maximum. If you want to know the area that becomes, then you could use a equals xy or a equals x times that expression to figure out what is the area, but they didn't ask what the area is, okay? I'm just going to show you how to do that with the calculator now. So I go to the y equals screen, and then I'm going to put this equation in here, and instead of a, of course, I'm going to use y1, and instead of the x, little x's, I use big x's. This is one of the most confusing parts about it, right? Because you have to reassign the variables so that they're the exact same variables that the calculator is using. I put my negative 9/8 in parentheses because I don't want things to be unexpectedly put in the denominator that I didn't intend to. You can use that vertical fraction too, the math number vertical fraction. That's also a good way of making sure that you don't put things in the denominator that you didn't want to. And then I'm going to graph it. And it's like not on the screen. And whenever that happens, you shouldn't say, oh my gosh, the thing didn't graph. It's actually off the screen, right? Because like, look how big the values we're using are. They're like hundreds, right? And in this particular case, we are only showing negative 10 to 10. So let's take the window and let's make the thing into 100. So we're talking about hundreds of meters. So let's, instead of negative 10 to 110, let's put negative 10 to 100. Why didn't I put negative 100? Well, we know that the lengths are not going to be negative, so we might as well just concentrate on hundreds. So let's put like 500 maybe. So put 500 for x max, and then we'll graph again. Okay, now it looks like a straight line instead of like a parabola. Why is that? Because do you see how the vertical is still negative 10 to 10? The area, we're talking thousands, right? Because if you multiply lengths that are 100 times each other, you're getting like a huge, huge number that's in the thousands. So we don't know exactly how big that is, but we could do zoom fit. Zoom fit, which is option 0, I think. Zoom fit is like one of the most useful options, and it's like the farthest away from the initial position there. Okay, that's a little bit better. But like, we don't need this negative part because we don't care about negative areas. So we'll go back to window again, and then we'll change the y min, which is now negative 168,000. We're going to change that to like, you know, negative 10. Okay, now it's perfect. Now we want to know what is the vertex. So we can find the vertex by doing second calc max, right? Because in this case, the vertex is a max point. So first it says, what's the left boundary? We move the cursor to the left. Oh, there's the cursor. And I'm going to move the cursor to the left of the vertex. And I hit enter. And then I move the vertex to the right of the vertex. And then I hit enter. And then it asks me for a guess. Doesn't matter what the guess is. And the maximum value is 99.9999, which is 100. And the area turns out to be 11,250. That's the value that they didn't ask for. You can calculate if you want to. So the answer is x equals 100. That's what we got when we did it by hand using negative b over 2a, right? And the y value turned out to be 112.5, which the calculator is not showing us because the calculator only shows us the x value and the a value because that's what it's graphing, right? All right, let's move on. The graph of y equals x squared minus 3x and y equals 2x minus x squared are illustrated without using technology. Show that the graphs meet where x equals 0 and x equals 2.5. Find the maximum vertical separation between the curves for the x values between 0 and 2.5. Okay. So this one is 2x minus x squared. Makes sense because it's got a negative x squared, so it's a upside down parabola. And this one is x squared minus 3x. Actually, what I'm going to do is I'm going to code these in colors. So that one's going to be red, and this one's going to be blue. All right, so this one's going to be blue. This one's going to be red. Show that the graphs meet where x equals 0 and x equals 2.5, and they want us to do that without the calculator. Well, to find the intersection points, these points here, what we need to do is we need to set them equal to each other, because at these intersection points the x and y values are exactly the same. So when I assume that this y value is the same as the other y value, I can set the right sides equal to each other, okay? And that's the trick to finding the intersection points. Equals 2x minus x squared. And so how do we solve an equation like this with quadratic terms and linear terms, x squared terms and x terms? We could just put everything on the left side and make one big quadratic with 0 on the right side, and then we solve for the x-intercepts, right? So what we're going to do is we're going to subtract, or we're going to add x squared to both sides so that we get x squared on the left only. We're going to subtract 2x from both sides to get the x terms on the left only. And then we'll get 2x squared minus 5x equals, and then the right side becomes 0. So 2x squared minus 5x equals 0. That is a parabola, and we want to know when that parabola equals 0, and that would give us the answer as to what are the x values of those two intersection points. So remember, to solve this equation, we can either factor, which most of the time I don't recommend doing, or we can do quadratic formula. In this particular case, though, factoring is effortless, right? If you factor out a 2 here, you get 2x minus 5. You don't need to do any real thinking to do this factoring. And what that tells us is the possible values of x which make this expression 0 would be, if this was 0, the whole thing would be 0, because 0 times something is 0. And 2x minus 5, if that expression was 0, then that would also make the whole thing 0. So I'm going to add 5 to both sides. I get 2x equals plus 5. And then I'm going to divide both sides by 2. I get x equals 5 halves. X equals 5 halves. So x equals 5 halves and x equals 0 are the two solutions. Those are the two places that the two curves cross each other. Okay, so that was part A. Part B, if you want to know the y value where these two intersect, you just take 0 and you put it into the red equation or the blue equation. You can see you'll get 0, right? And if you want to see where the y value is for this, then you take 5 halves and you put it in either one of the equations also. Okay, but they didn't ask us for that. So that was A. What about B? Find the maximum vertical separation between the curves. Okay, so how do I measure vertical separation? So if I'm going to color code these again. So this is going to be the red curve, right? And this is going to be the blue curve. Do you see how the blue curve between those two intersection points is always greater than the red curve? So if I wanted to find the distance between the blue curve and the red curve at any point, I could just take the blue y value, which we could say is 2x minus x squared, and I could subtract the red y value, which is x squared minus 3x. Okay, and then I am going to simplify. So this is the yellow bar length here, okay? So I would get, I'm going to combine the 2x with the, let's do this first. Well, let's distribute that. So I'm going to distribute the negative sign, and I get that. And then I'm going to combine the two x squareds, and I'll get negative 2x squared. And then I'm going to combine the 2x to the 3x, and I'll have plus 5x. So that is my expression for the yellow length. So they said find the maximum yellow length depending on the value of x, right? So I got this. So when is this maximum? Well, they said not. Well, I don't know if they don't want us to use the technology for part B, But remember that this is an upside down parabola because a equals -2, right? And so to find the x value which makes this quantity the largest, all we need to do is find x equals -b over 2a. So this is a, right? -2, and this is b, which is 5, and c, of course, is 0. So -5 over 2 times -2, which is -5 over -4, which is 5/4. So the x value, which makes the blue minus red distance the greatest, is 5/4. And that's it.